Hello, dear traveler of the night. Some nights the universe feels closer than it should. Stars pulse in rhythm with your breath. Silence becomes something you can almost touch. Maybe that's what happens when the mind stops asking questions and simply listens to the dark. Tonight we're going to drift into a question so strange, so quietly impossible, that even physicists whisper when they speak of it. Did the Big Bang truly begin? Or did something else come first? Something so small, so brief, that time itself forgot how to measure it. Before we slip into this mystery together, I want to thank you for being here, for choosing silence over noise, wonder over answers. If you find comfort in these quiet journeys through the cosmos, you might like to stay a while. You can gently tap the like button, subscribe, if you'd like more stories told softly. And ring the little bell, not for noise, but so the next quiet night can find you again. Your presence here means more than you know. Now let's drift. Tonight we're traveling to the edge of existence itself. Not the edge of space, but the edge of meaning. The place where every law we know, every equation we trust, dissolves into something physicists call the Planck scale. It's a boundary written in mathematics, whispered in quantum equations, and hidden at the very beginning of everything. If the Big Bang was the universe's first breath, then the Planck scale was the silence before the inhale. A moment so unimaginably small that calling it a moment feels almost like lying. Imagine this. You're standing at the shore of an ocean. The waves roll in, steady and rhythmic. Each wave arrives, breaks, retreats. You can count them. You can time them. But now imagine you walk backward away from the water, through time itself, watching the ocean reverse. The waves unbreak. The tide pulls inward. The ocean shrinks, and you keep walking backward through billions of years, past the formation of Earth, past the birth of the sun, past the ignition of the first stars. You walk until there are no stars at all, no galaxies, no light. Just energy raw and formless, compressed into a space smaller than an atom, smaller than a nucleus, smaller than anything we have words for. And then you reach it, the Planck scale, a frontier where physics doesn't just struggle, it surrenders. The Planck scale isn't a place, it's a threshold, a measurement so extreme that below it, the concepts of distance, time, and even causality lose their meaning. Scientists describe it as the smallest possible length, 1.6 times 10 to the negative 35 meters. To put that in perspective, if you scaled an atom up to the size of the observable universe, the Planck length would still be smaller than a human hair. It's not just small, it's the definition of small, the full stop at the end of the sentence of size. This scale was named after Max Planck, a German physicist who never intended to revolutionize the universe. In 1900, Planck was trying to solve a simple problem about how heated objects emit light. He introduced a tiny constant into his equations, just a number he thought a mathematical tool. But that constant now, called Planck's constant, became the key to unlocking quantum mechanics. It revealed that energy doesn't flow smoothly like water. It comes in packets and chunks, in discrete little bursts. The universe, it turns out, is grainy at its core. And if energy is grainy, then so is everything else. Space, time, reality itself. This is where things become strange. Beautifully, impossibly strange. Because if there's a smallest possible length, then there's also a smallest possible time. Planck time. It's the duration it takes for light to cross one Planck length in a vacuum. That's about 5.4 times 10 to the negative 44 seconds. To say that out loud feels almost disrespectful to the number. It's not a blink, it's not even a fraction of a blink. It's the quantum flutter before anything can be said to have happened. Before this moment, before Planck time, the word before loses meaning. Time as we understand it doesn't exist yet. There's no clock to measure it, no sequence of events to remember. Just a kind of pre-existence, a twilight state that our brains can't fully picture because we are beings who live inside time. We swim in it. We breathe it. And yet, at the very beginning, time itself had to be born. This is the paradox cosmologists face when they try to describe the Big Bang. They can tell you what happened 1 second after it began. They can map the universe at 3 minutes old when the first hydrogen nuclei formed. They can show you the cosmic microwave background, the faint glow of the universe at 380,000 years old, still warm from its fiery birth. But when you ask them what happened at the very first instant at time zero, they pause, they hedge. They admit that the mathematics breaks down. Albert Einstein gave us general relativity, a magnificent theory that describes gravity as the curvature of space-time. It works beautifully for planets, stars, galaxies, even black holes. But at the Planck scale, relativity stumbles. Quantum mechanics gave us a framework for understanding particles' energy and probability at the smallest scales. It works beautifully for atoms, electrons, photons. But when you try to apply it to gravity, to the warping of space-time itself, quantum mechanics stumbles too. The two great pillars of 20th century physics, relativity and quantum mechanics, both reach their limits at the same place, the Planck scale, the beginning. So, what does that mean for the Big Bang? Did it truly begin at the Planck scale? Or is the idea of a beginning just a story we tell because our minds crave origins, first causes moments when the clock starts ticking? Some physicists suggest the Big Bang wasn't a beginning at all, but a transition. A moment when something even stranger, something we don't yet have words for, gave way to the expanding universe we observe today. There's a hypothesis called the Big Bounce, which suggests that before the Big Bang, there was a previous universe. It collapsed inward, crushed under its own gravity, until it reached the Planck scale and, like a rubber ball hitting the ground, bounced back. Our universe in this view is just the rebound, the exhale after an inhale. One cycle in an eternal rhythm of cosmic breathing. Then there's the idea of quantum foam proposed by physicist John Wheeler in the 1950s. At the Planck scale, space-time itself might not be smooth and continuous. It might be bubbling, frothing, filled with tiny wormholes and fluctuations that appear and disappear faster than thought. In this foam, the very notion of here and there, now and then, becomes fluid. Reality at its deepest level might be less like a stage and more like an ocean, always moving, never still. And perhaps most humbling of all is this: we may never know. Not because we lack curiosity or intelligence, but because the Planck scale represents a genuine limit to what can be observed. To probe it directly, you'd need an accelerator the size of the Milky Way. You'd need energy concentrations that would collapse into black holes before they could reveal anything. The universe, in a sense, guards its secrets. It allows us to peek into the first few minutes after the Big Bang, but the first instant that remains veiled. Does that frustrate you, or does it comfort you? There's something quietly profound about limits. They remind us that not everything is meant to be solved, dissected, conquered. Some mysteries are meant to remain mysteries, not because they're unsolvable, but because they're sacred. The Big Bang. If it began at the Planck scale, began in a place beyond measurement, beyond observation, beyond the reach of human hands. It began in a silence so deep that even light hadn't learned to shine yet. Think about that for a moment. Before the Big Bang, there was no light. No darkness either, because darkness is just the absence of light, and you need space for absence. There was no space, no stage for anything to happen on, no clock for anything to happen in. Just potential. Just the mathematical possibility of existence, humming quietly in a dimension we can't fully imagine. And then somehow, that potential became real. The universe inflated from smaller than a grain of sand to larger than a galaxy in a fraction of a second. Energy flooded into being. Particles condensed from pure heat. Forces separated. Gravity pulled. Electromagnetism sparked. And in that first wild, chaotic rush, the seeds of everything were planted. Stars, planets, life, you. You sitting here now, breathing softly, listening to this story, are made of atoms forged in the hearts of stars that died billions of years ago. But those atoms trace their lineage back even further, back to the first 3 minutes of the universe when hydrogen and helium, condensed from the primordial fireball. And those elements trace back to the Planck epoch, that first incomprehensible instant when the universe was so hot, so dense that matter as we know it couldn't exist yet. Only energy, only potential. You are the Big Bang still happening, still expanding, still cooling, still becoming. But here's the question that pulls at the edges of thought. If the Big Bang began at the Planck scale, what set it in motion? What lit the fuse? Was it a random quantum fluctuation, a glitch in nothingness that suddenly became everything? Was it inevitable, written into the mathematics of existence itself? Or was there something before, something outside the equations? Outside time, outside the boundaries of what physics can describe? These aren't just scientific questions. They're philosophical ones, spiritual ones even. They sit at the intersection of cosmology and wonder where facts blur into poetry and equations become prayers. The Planck scale is where science meets humility, where knowledge bows before mystery. And maybe that's exactly as it should be, because the universe didn't ask us to understand it. It simply invited us to witness it, to stand beneath the stars and feel small, to ask questions that have no answers and find beauty in the asking. Tonight we've begun our journey at the very edge of that invitation. We've touched the boundary where time forgets how to begin. But this is only the opening. The universe has so much more to whisper. In the moments ahead, we'll explore what the Planck length truly means, why it's the smallest ruler we'll ever know, and how it shapes everything from black holes to the fabric of space itself. We'll drift through the mathematics of mystery, the physics of impossibility, and the quiet, stubborn hope that maybe we can glimpse the face of creation. But for now, rest in this. The Big Bang may have begun at the Planck scale, or it may have emerged from something even stranger. Either way, you are here. The universe took 13.8 billion years to arrange atoms into the shape of you, into someone capable of asking these questions, of feeling this wonder. That alone is extraordinary. So, breathe. Let the stars do their work. And let's continue gently into the smallest distances the cosmos will allow. We measure everything: the distance to the moon, the width of a hair, the wavelength of light. We build rulers, microscopes, satellites, tools to pin down the universe in numbers we can hold. But what if I told you there's a length so small that measuring anything smaller becomes meaningless, not difficult, not impossible with better technology, meaningless. A place where the very concept of distance dissolves like sugar in water. That length exists. Physicists call it the Planck length. And it's the smallest ruler we'll ever know. Let's begin where this story truly starts, with a man who never intended to find the universe's limits. Max Planck was born in 1858 in Kiel, Germany, into a family of scholars and lawyers. He was methodical, conservative in his thinking, and deeply respectful of classical physics. In fact, when he was a young student considering a career in physics, one of his professors told him there was nothing left to discover. All the great questions had been answered. The universe, they believed, was a solved puzzle. Planck didn't listen. Or perhaps he did, but the universe had other plans. In 1900, Planck was wrestling with a problem that had frustrated physicists for years. It was called the ultraviolet catastrophe, a fancy name for a simple mystery. When you heat an object, it glows. First red, then orange, then white hot. Classical physics predicted that as the temperature increased, the object should emit infinite amounts of ultraviolet light. But that didn't happen. Hot objects glowed, yes, but they didn't explode into infinite radiation. Something was wrong with the equations. Planck found the solution, but it cost him his worldview. He introduced a constant, a tiny number, into his formula. This constant suggested that energy doesn't flow continuously like a river. It comes in packets, discrete chunks, quanta. The word itself means how much, a unit, a piece, a boundary. Planck himself didn't believe it at first. He called it a mathematical trick, a desperate act to make the numbers work. But the trick turned out to be true. That constant, now called Planck's constant, is written as h. Its value is approximately 6.626 times 10 to the negative 34 joule seconds. It seems abstract, almost meaningless in daily life. But from this single number, you can derive the fundamental limits of reality, the smallest distance, the shortest time, the faintest possible action. Planck's constant is the universe's way of saying this far and no further. The Planck length is one of those limits. It's calculated by combining three fundamental constants of nature: Planck's constant, the speed of light, and the gravitational constant. When you weave these together mathematically, you get a length of approximately 1.616 times 10 to the negative 35 meters. To write that out in full would take 35 zeros after the decimal point before you reach the 1. It's a number so small that it makes atoms look like galaxies. Here's a comparison that might help though. Even comparisons struggle at this scale. An atom is about 10 to the negative 10 meters across. That's already tiny millions of them fit on the period at the end of a sentence. A proton nestled in the atom's nucleus is about 10 to the negative 15 meters, smaller still. But the Planck length is 10 to the negative 35 meters. That means a Planck length is to a proton what a proton is to, well, there's no everyday object that fits the analogy. The gap is too vast. Let me try another way. Imagine you could magnify a Planck length until it was the size of a marble. On that same scale, a single hydrogen atom would be larger than the observable universe. Not the Milky Way, not a galaxy cluster. The entire observable universe, 93 billion light years across. That's how small the Planck length is. It's not just small, it's the edge of smallness. But why does this length exist? Why can't we measure something smaller? The answer lies in one of the strangest principles in quantum mechanics, Heisenberg's uncertainty principle. Werner Heisenberg discovered in 1927 that there's a fundamental limit to how precisely we can know certain pairs of properties. The more accurately you measure a particle's position, the less you can know about its momentum. The more you pin down where something is, the less you can say about where it's going. This isn't about bad instruments or clumsy experiments. It's built into the fabric of reality. At the quantum scale, particles don't have definite positions until you measure them. They exist as clouds of probability smeared across space. And when you try to measure something at the Planck scale, the uncertainty becomes total. To probe distances that small, you'd need to concentrate so much energy into such a tiny space that you'd create a black hole. The very act of measurement would destroy the thing you're trying to measure. Think about that. The universe has a built-in privacy shield. There are things it will not let you see, not because you lack the tools, but because seeing them would violate the laws of physics themselves. This leads to one of the most radical ideas in modern physics: space might not be continuous. We think of space as smooth, like a sheet of glass, infinitely divisible. You can always cut a distance in half and then half again and again forever. But what if that's wrong? What if space is granular, made of tiny indivisible pixels, each one Planck length across? What if the universe at its deepest level is more like a digital screen than a watercolor painting? This idea is called quantum geometry, and it's at the heart of theories like loop quantum gravity. In this view, space-time isn't a backdrop on which events occur. It's made of something quantum loops of space woven together like threads in a fabric. Each loop is roughly Planck-sized. You can't zoom in any further because there's nothing smaller to zoom into. It's the bottom of the rabbit hole. Some scientists describe this as space-time foam, a term coined by John Wheeler. If you could somehow magnify space to the Planck scale, it wouldn't look smooth and still. It would be roiling, bubbling, fizzing with quantum fluctuations. Tiny wormholes might flash into existence and vanish in less than Planck time. Virtual particles would swarm like fireflies, borrowing energy from the vacuum and paying it back before the universe notices. Space at this scale is alive, restless, a sea of quantum noise. But how do we know any of this is real? We can't see it. We can't measure it directly. We can't build a microscope powerful enough to zoom into the Planck scale. So, why believe it? The answer is consistency. The mathematics that predicts the Planck length also predicts things we can test. Quantum mechanics. Despite its strangeness, is the most accurate scientific theory ever devised. It predicts the behavior of electrons, the spectrum of light, the structure of molecules, down to more than 10 decimal places of precision. General relativity. Einstein's theory of gravity predicts the orbits of planets, the bending of light around stars, the existence of black holes, all confirmed by observation. Both theories point toward the Planck scale as a boundary. They agree on this, even though they disagree on almost everything else. And there's another clue, subtle but profound. In the 1940s, a Dutch physicist named Hendrik Casimir predicted a strange effect. If you place two uncharged metal plates very close together in a vacuum, they should attract each other. Not because of gravity or magnetism, but because of quantum fluctuations in the vacuum itself. The space between the plates is so narrow that only certain wavelengths of virtual particles can fit. Outside the plates, all wavelengths are possible. This creates a pressure difference and imbalance that pushes the plates together. It sounds absurd, empty space pushing on metal. But in 1997, physicist Steve Lamoureux measured the Casimir effect with exquisite precision, and it matched the predictions exactly. The vacuum isn't empty. It seethes with energy, with potential, with quantum whispers. And if that's true at scales we can measure, why wouldn't it be true at the Planck scale? There's a deeper lesson here, one that goes beyond equations. For most of human history, we believed that if we look closely enough, we'd find the ultimate building blocks of reality. The Greeks imagined atoms indivisible particles that couldn't be cut any further. They were wrong about atoms, but right about the instinct. There should be a bottom, a foundation, a final answer. The Planck length might be that answer. Not a particle, but a limit. Not a thing, but a threshold. It tells us that reality has a resolution like a photograph. Zoom in too far, and the image pixelates, meaning dissolves. The Planck scale is where the universe says this is as deep as the question goes. But here's the paradox. The Planck length is unimaginably small, yet it might define the largest structures in the cosmos. Black holes, for example, have event horizons boundaries beyond which nothing, not even light, can escape. The surface area of a black hole's event horizon measured in Planck areas might determine how much information the black hole contains. This idea, called the holographic principle, suggests that all the information in a volume of space can be encoded on its boundary like a 3D image projected from a 2D surface, and the pixels of that projection Planck-sized. Even the Big Bang itself might be written in Planck units. If the universe began at the Planck scale, then the first structures, the first ripples of density that would one day become galaxies might have been imprinted at that moment. The cosmic microwave background, the afterglow of the Big Bang, shows tiny variations in temperature across the sky. Those variations are the seeds of everything we see today, and their origin might trace back to quantum fluctuations at the Planck epoch, magnified by the explosive expansion of space. Think about what that means. The pattern of galaxies across billions of light years might be the echo of quantum noise from a time when the universe was smaller than a single atom, the largest structures in existence shaped by the smallest possible scale. It's a kind of cosmic poetry order, emerging from chaos infinity, born from infinitesimal. But the Planck length also confronts us with our limits. There are questions we might never answer, not because we're not smart enough, but because the universe won't let us. What happened before the Planck epoch? What lies beneath the Planck length? These might be questions without answers, not because the answers don't exist, but because the questions themselves dissolve at that scale. Language fails, logic bends. Even mathematics, our most precise tool, starts to stutter. And maybe that's okay. Maybe the Planck length is the universe's way of teaching us humility. There are boundaries we weren't meant to cross, mysteries we weren't meant to solve, not because they're sacred or forbidden, but because they're beyond the framework of measurement and meaning. The Planck scale is where physics meets philosophy, where science meets silence, So, what do we do with that? Do we stop asking questions? No, we ask differently. We accept that some answers will always be approximations, shadows of truths too deep to grasp fully. And in that acceptance, there's a strange kind of freedom. We don't need to know everything. We just need to wonder well. The Planck length is the smallest ruler we'll ever know, but it measures more than distance. It measures the limits of knowledge, the boundaries of curiosity, the edge of what can be said. And beyond that edge, there's only the quiet hum of existence, the wordless fact of being. We've touched the smallest distance now. We've held infinity in our hands and felt it slip through our fingers. But distance is only half the story. Because if there's a smallest length, there must also be a smallest time, a moment so brief that calling it a moment feels like an exaggeration. That's where we turn next into the heartbeat of creation itself, the first tick of existence. If you could stop time for just 1 second, you'd experience approximately 10 to the 44 Planck time units passing through your frozen moment. That number is so large it has more zeros than there are atoms in your body. And yet each of those units, each Planck time, is the shortest duration that has any meaning in our universe. Shorter than that, and time itself becomes a word without definition. We've found the smallest distance. Now, we hold the briefest moment. And in that moment, the universe was born. The Planck time is calculated the same way as Planck length by weaving together the fundamental constants of nature. Take Planck's constant divide by the speed of light squared, multiply by the gravitational constant, then take the square root. What emerges is approximately 539 times 10 to the negative 44 seconds. To understand how small that is, consider this. There are more Planck times in 1 second than there have been seconds since the Big Bang. Time at its foundation is not smooth. It ticks. It pulses. It comes in grains so fine that infinity seems to live between them. But what does it mean for time to have a minimum unit? We're so accustomed to thinking of time as a river flowing endlessly, infinitely divisible. You can always imagine half a second, then half of that, then half again. But the Planck time suggests otherwise. Below this threshold, the concept of before and after loses coherence, causality. The idea that one event leads to another begins to dissolve. At the Planck scale, time might not flow at all. It might flicker like frames in a film reel, each one discrete, separated by a gulf too small to measure, but real nonetheless. This has profound implications for the Big Bang. Cosmologists can trace the history of the universe backward with remarkable precision. They can tell you what conditions were like 1 second after the beginning, when the temperature was about 10 billion degrees, and the universe was a soup of neutrons, protons, electrons, and photons. They can go further back 1 millisecond, 1 microsecond, even 1 nanosecond. But when they reach Planck time, the story stops. Not because we lack data, but because the laws of physics themselves break down. At 539 times 10 to the negative 44 seconds after the Big Bang, the universe was unimaginably hot and dense. The temperature is estimated to have been around 10 to the 32 Kelvin, a number so extreme that all 4 fundamental forces of nature were unified into a single force: gravity, electromagnetism. The strong nuclear force and the weak nuclear force weren't separate yet. They were one. Physicists call this state a unified field, a kind of primordial symmetry that existed only in that first instant before breaking apart into the distinct forces we observe today. But here's the paradox. To describe what happened during Planck time, you need a theory that combines quantum mechanics and general relativity. You need a theory of quantum gravity. And we don't have one. Not yet. General relativity describes gravity as the curvature of space-time, smooth, continuous, geometric. Quantum mechanics describes reality as probabilistic, discrete, uncertain. At large scales, relativity works perfectly. At small scales, quantum mechanics works perfectly. But At the Planck scale, where gravity becomes as strong as the other quantum forces, the two theories contradict each other. Einstein spent the last 30 years of his life searching for a unified theory. He wanted to weave gravity and electromagnetism into a single framework, convinced that the universe must be fundamentally simple, elegant, governed by one beautiful equation. He failed. Not because he wasn't brilliant, he was, but because the problem is harder than even he imagined. Quantum mechanics, which he never fully accepted, turned out to be essential, and gravity, his greatest achievement, refused to play nicely with quantum rules. Stephen Hawking and Roger Penrose proved in the 1970s that if general relativity is correct, then the Big Bang must have begun at a singularity, a point of infinite density where all the matter and energy in the universe was compressed into zero volume. Mathematically, singularities are places where equations blow up, where numbers become infinite, where predictions break down. Physicists hate singularities. They're like cracks in the foundation of reality, signs that something in the theory is incomplete. So, did the Big Bang truly begin at a singularity? Or is the singularity just a placeholder, a signal that our mathematics has reached its limit? Most physicists today believe the latter. They suspect that quantum effects, which general relativity ignores, would have smoothed out the singularity. Instead of infinite density, there might have been a smallest possible volume, roughly 1 cubic Planck length. Instead of infinite curvature, there might have been a maximum curvature, a point where space couldn't bend any tighter. This is where Planck time becomes crucial. If the universe didn't begin at a singularity, then it began at Planck time. Before that moment, if before even makes sense, there was no time. No sequence of events, no cause and effect. The universe wasn't sitting in darkness, waiting to explode. It wasn't sitting anywhere. There was no where. There was no when. There was only potential, a kind of quantum blur, where existence and non-existence overlapped. Some cosmologists describe this as a quantum fluctuation. In quantum mechanics, empty space isn't truly empty. It's filled with virtual particles, pairs of particles, and antiparticles that flash into existence borrowed from the vacuum and annihilate each other almost instantly. These fluctuations are real. We've measured their effects in laboratories. The Casimir effect, which I mentioned earlier, is one example. Another is the Lamb shift, a tiny change in the energy levels of hydrogen atoms caused by virtual photons flickering in and out of existence. If the vacuum can produce particles, could it produce a universe? Alexander Vilenkin, a cosmologist at Tufts University, proposed exactly that in the 1980s. He suggested that the universe could have tunneled into existence from nothing, not from empty space, but from true nothingness, a state with no space, no time, no laws. Quantum mechanics allows for this kind of tunneling. Particles do it all the time, passing through barriers they shouldn't be able to cross, according to classical physics. So, why not a universe? It sounds absurd, almost mystical, a universe from nothing, but the mathematics is rigorous. Vilenkin showed that in quantum cosmology, the probability of a universe tunneling into existence is not zero. It's small, yes, but not impossible. And if the probability is not zero, and if you wait long enough, though waiting doesn't make sense without time, then eventually it happens. A universe sparks into being, and once it exists, inflation takes over, blowing it up from Planck size to astronomical size in a fraction of a second. But this raises a troubling question. What is time before time exists? During Planck time, the universe was so small and so energetic that quantum uncertainty dominated everything. Time, like space, would have been subject to quantum fluctuations. It might have branched, looped, blurred. Imagine trying to set a clock in a place where seconds don't pass, in order where cause doesn't necessarily precede effect, where the past and future are entangled like particles in a quantum state. This isn't science fiction. It's a consequence of applying quantum mechanics to cosmology. When you solve the equations describing a quantum universe, you get something called the Wheeler-DeWitt equation. named after John Wheeler and Bryce DeWitt. This equation describes the quantum state of the entire universe. But here's the strange part. The equation has no time variable. Time doesn't appear in it. The universe from a quantum perspective is timeless. All moments exist simultaneously like notes in a chord rather than a melody. So, where does the time we experience come from? Why does it feel like time flows, like the past is fixed and the future is open? One possibility is that time is emergent. It's not fundamental, but a feature that arises from deeper timeless laws. Think of it like temperature. Temperature is real, you feel it, you measure it, but it's not fundamental. It emerges from the motion of trillions of molecules. Maybe time works the same way. Maybe it emerges from the quantum behavior of the universe as a whole, and at the Planck scale where the universe is smallest time hasn't fully emerged yet. This is deeply unsettling. We are beings who live in time. We remember the past, anticipate the future, experience the present as a moving moment. To imagine a state where time doesn't exist feels like imagining a color beyond the visible spectrum, a sound beyond hearing. And yet, if the Big Bang began at Planck time, then there was a moment, a proto-moment, when time itself was just beginning to be. Think about what that means for causality. We're used to asking what caused the Big Bang, what lit the fuse, what set the universe in motion. But these questions assume time already exists. They assume there's a before that leads to an after. If time itself began at the Planck epoch, then asking what came before is like asking what's north of the North Pole. The question doesn't make sense. Not because we don't know the answer, but because the question is built on a faulty assumption. St. Augustine wrestled with this in the 4th century. People asked him what was God doing before he created the universe. Augustine's answer was brilliant. He said there was no before. Time was created along with the universe. Before creation there was no time, so the word before has no meaning. 14 centuries later, physicists arrived at the same conclusion through completely different reasoning. Time and space are not containers that exist independently. They're part of the universe woven into its fabric. When the universe began, time began. But this leads to another puzzle. If Planck time is the shortest meaningful duration, does that mean time is quantized? Does it tick forward in discrete jumps, like a cosmic stopwatch clicking from one Planck time to the next? Some theories suggest yes. In loop quantum gravity, space-time is built from tiny loops, each representing a quantum of space and time. These loops don't sit in space and time, they are space and time. And if space comes in chunks, then time must too. Other theories say no. String theory, for example, treats space-time as smooth, even at the Planck scale, though it adds extra dimensions curled up too small to see. In string theory, particles aren't points, but tiny vibrating strings, and their vibrations determine what kind of particle they are. An electron is one vibration pattern, a photon another. Gravity itself is the vibration of a particular kind of string called a graviton. String theory can describe what happens at Planck energies without breaking down, but it does so by replacing points with strings, smoothness with vibration. The truth is, we don't know yet. Both loop quantum gravity and string theory are incomplete. Neither has made predictions we can test directly. We can't build a particle accelerator powerful enough to probe Planck-scale physics. It would need to be the size of the Milky Way galaxy, require more energy than all the stars in the universe produce, and likely collapse into a black hole before it could reveal anything. The Planck scale is in a very real sense beyond our reach. And maybe that's the point. Maybe the universe has limits not to frustrate us, but to define us. We are beings of scale. We exist comfortably between the very large and the very small, between galaxies and atoms, between eons and instants. The Planck scale is the basement of reality, the foundation we stand on, but can never dig beneath. And Planck time is the first beat of the drum, the moment when rhythm began, even if we can't hear the silence before it. So, when we ask, did the Big Bang begin at the Planck scale? What we're really asking is, Did the universe have a true beginning, or is beginning just a word we use because we can't see further back? The answer might be both. The Big Bang began at Planck time, in the sense that time itself started ticking. But what set it ticking? What wound the clock? Those questions may not have answers, not because we're not clever enough, but because they exist outside the framework of time and causality altogether. There's a strange comfort in that. Not knowing doesn't mean we've failed. It means we've reached the edge of what knowing is. And at that edge, we find something other than knowledge, humility, wonder, reverence for the mystery itself. Planck time is the shortest tick of existence. It's the boundary between being and becoming, between nothing and everything. And it marks the moment when the universe took its first breath. But breath requires space to move through laws to govern it, forces to shape it. And those forces, those laws were not always separate. They were once one unified perfect, until something broke the symmetry and the universe as we know it began to unfold. There's a place in the universe where Einstein's equations stop working, not because they're wrong, but because they're incomplete, where gravity becomes so intense, so concentrated, that the smooth curves of space-time shatter into quantum static. It's the place where the two greatest theories of the 20th century, general relativity and quantum mechanics, meet each other like strangers speaking different languages, unable to agree on what's real. That place is everywhere at the Planck scale. And it's the reason we still don't understand the beginning. Albert Einstein published his general theory of relativity in 1915. And it changed everything. Before Einstein, gravity was a force, something that pulled objects toward each other across empty space. Newton's equations worked beautifully for planets, moon's apples falling from trees. But Einstein saw deeper. He realized that gravity isn't a force at all. It's geometry. Mass and energy curve the fabric of space-time, and objects move along those curves the way a marble rolls along a bent sheet of rubber. The sun doesn't pull the Earth toward it. The sun warps space-time, and the Earth follows the curve. General relativity predicts things that seem impossible. It says that time runs slower near massive objects. Clocks on Earth tick slightly slower than clocks on satellites because Earth's gravity warps time itself. GPS systems have to account for this, or they'd be off by miles. Einstein's theory predicts black holes regions where space-time curves so sharply that nothing, not even light, can escape. For decades, physicists thought black holes were mathematical curiosities, not real objects. But we've found them now, thousands of them. We've even photographed one, a supermassive giant at the center of the galaxy, M87, its shadow rimmed by light, bent into a ring by gravity's grip. General relativity is one of the most successful theories in science. It describes the motion of galaxies, the expansion of the universe, the ripples in space-time, called gravitational waves, that LIGO detected in 2015. At large scales, planets, stars, galaxies, it works flawlessly. But at small scales, it fails, not gradually, but catastrophically. Quantum mechanics, on the other hand, governs the very small. It emerged in the early 1900s from experiments that classical physics couldn't explain. Light behaves like both a wave and a particle. Electrons don't orbit atoms the way planets orbit stars. They exist in clouds of probability appearing here or there only when measured. Energy comes in discrete packets. Position and momentum can't both be known precisely. The act of observation changes what's being observed. Quantum mechanics is strange, counterintuitive, almost magical. Einstein himself never fully accepted it. He famously said, "God does not play dice with the universe," rejecting the idea that reality is fundamentally probabilistic. Niels Bohr, one of the founders of quantum theory, replied, "Einstein stopped telling God what to do." But despite Einstein's objections, quantum mechanics proved itself again and again. It explains the behavior of atoms, the structure of molecules, the way electrons flow through circuits. Without quantum mechanics, we wouldn't have transistors, computers, smartphones, lasers, or most of modern technology. At the scale of atoms and particles, quantum mechanics is king. But when you try to apply it to gravity, to the curvature of space-time itself, the math breaks. The equations produce infinities numbers that explode to meaninglessness. Physicists call this non-renormalizable. Other forces, electromagnetism, the strong and weak nuclear forces, can be described quantum mechanically. You can calculate the probability of a photon being emitted, an electron scattering a quark binding. But gravity resists. The gravitine, the hypothetical quantum particle that would carry the gravitational force, has never been observed. And the mathematics suggests it might be unobservable, buried beneath layers of complexity that no current theory can penetrate. This is the great unsolved problem in physics: how to unify general relativity and quantum mechanics. How to describe gravity at quantum scales. How to answer the question, what happens when space-time itself becomes uncertain? The place where this question becomes urgent is inside black holes. According to general relativity, a black hole's center is a singularity, a point of infinite density where space-time curvature becomes infinite. But infinity is a red flag. It means the theory has reached its limit. Quantum mechanics suggests that nothing can be truly infinite. There's always a smallest scale, a quantum of something. So, the singularity probably isn't real. It's a placeholder, a sign that we need a better theory. Stephen Hawking discovered something remarkable about black holes in 1974. He showed that black holes aren't completely black. They emit radiation now called Hawking radiation because of quantum effects near the event horizon. Virtual particle pairs, which normally pop into existence and annihilate each other instantly, can be split by the black hole's gravity. One particle falls and the other escapes. To an outside observer, it looks like the black hole is glowing, radiating energy. Over unimaginable timescales, trillions upon trillions of years, a black hole can evaporate completely. This discovery was profound because it showed that quantum mechanics and general relativity are both true, both necessary, but still incompatible. Hawking radiation requires both theories to work together, yet we don't have a framework that fully unites them. It's like having two puzzle pieces that clearly belong to the same picture, but no matter how you turn them, they won't fit. The problem becomes even more acute at the Planck scale. At normal energies, gravity is by far the weakest of the four fundamental forces. Electromagnetism is 10 to the 36 times stronger. The strong nuclear force, which holds quarks together inside protons, is even stronger. Gravity only dominates at large scales because it's always attractive and it adds up. A planet's gravity is the sum of trillions of atoms pulling together. But at the Planck scale, distances are so small and energy so high that gravity becomes as strong as the other forces. It can no longer be ignored. And that's where general relativity, which treats space-time as smooth and continuous, clashes with quantum mechanics, which treats everything as grainy and probabilistic. Imagine trying to describe an ocean wave. At large scales, you can treat the ocean as a smooth surface, rising and falling in gentle curves. That's general relativity, smooth, continuous, geometric. But zoom in close enough, and you see individual water molecules bouncing chaotically. That's quantum mechanics, discrete, probabilistic, uncertain. Both descriptions are true, but they use different languages. The challenge is finding a language that works at all scales, from molecules to waves to the entire ocean. Physicists have proposed several candidates for this unified language. The most famous is string theory. In string theory, particles aren't points, but tiny loops of energy, vibrating strings about a Planck length in size. Different vibration patterns create different particles. An electron is one note, a photon, another, a graviton, yet another. String theory can describe gravity at quantum scales without producing infinities, which is a triumph. But it comes with a cost. The equations only work consistently in 10 or 11 dimensions. We experience 3 dimensions of space and 1 of time. Where are the other 6 or 7 string theorists say they're curled up, compactified, into shapes so small we can't detect them? It's elegant mathematically, but frustratingly hard to test. Another approach is loop quantum gravity. Instead of replacing particles with strings, this theory suggests that space-time itself is quantized. Space isn't continuous, it's made of tiny loops woven together like chainmail. Each loop represents a quantum of space, roughly a Planck length across. Time too might be quantized, ticking forward in Planck-sized jumps. Loop quantum gravity doesn't require extra dimensions, which makes it simpler in some ways, but it struggles to incorporate the other forces of nature. Both theories are incomplete. Neither has made a prediction we can test directly, though researchers keep trying. Some hope to find evidence in the cosmic microwave background, the afterglow of the Big Bang, looking for tiny patterns that might reveal quantum structure in space-time. Others study black holes, hoping that observations of Hawking radiation or the behavior of matter near event horizons might offer clues. But here's what both theories agree on at the Planck scale: general relativity fails. Not because Einstein was wrong, he was brilliantly right, but because his theory was never meant to describe the quantum realm. It's a theory of smooth curves, not quantum jumps. And quantum mechanics, for all its success, was never meant to describe gravity. It's a theory of particles and forces, not the geometry of space-time. The Planck scale is where these 2 worlds collide, and in that collision, our understanding shatters. Think about what this means for the Big Bang. If we want to describe the universe at Planck time, when it was Planck-sized and Planck-hot, we need a theory that doesn't exist yet. We can trace the history of the universe back to 1/1000th of a second after the beginning. We can describe what happened at 1/1000000000th of a second. But that last moment, that first moment, the Planck epoch that remains veiled. Not because we lack telescopes or data, but because we lack the conceptual tools. Our equations break down. Our theories go silent. This isn't a failure, it's a frontier. Every great theory in history has had limits. Newton's laws couldn't explain the orbit of Mercury or the bending of light. Einstein's relativity completed what Newton began. Someday, a new theory will complete what Einstein began. We call it the theory of everything, or quantum gravity, or whatever name sticks. But the name doesn't matter. What matters is that we're honest about what we don't know. And we don't know what happens when space-time itself becomes uncertain. We don't know if space is continuous or discrete. We don't know if the Big Bang began at a singularity or smoothed out by quantum effects. We don't know if there's something smaller than the Planck scale, some deeper layer of reality we haven't imagined yet. What we do know is this: the universe doesn't care about our ignorance. It began anyway. It expanded anyway. It cooled, condensed formed stars and planets, and eventually, us. Somehow, despite the fact that our best theories contradict each other, at the most crucial moment, the universe figured it out. Maybe that's the real lesson. The universe is under no obligation to make sense to us. It doesn't owe us a theory of everything. It simply is, and we do our best to understand it with the tools we have. When those tools fail, we build better ones. We ask new questions. We accept that some answers will take generations to find, and some might never be found at all. Einstein spent the last 3 decades of his life searching for a unified theory. He wanted to merge gravity and electromagnetism into a single elegant framework. He covered blackboards with equations, filled notebooks with calculations, but never found the answer. When he died in 1955, his quest remained unfinished. Some saw this as tragic a genius defeated by an impossible problem. But maybe it wasn't defeat. Maybe it was devotion. Einstein knew he might not solve it, but he kept searching because the question mattered. That's what physics is at its best. Not the discovery of answers, but the courage to ask questions that might not have answers, or at least not yet. The Planck scale is one of those questions. It's the place where Einstein met his limit, not because he failed, but because he succeeded so completely that he revealed the next horizon. And beyond that horizon, something waits. Not a singularity, perhaps, but a new way of thinking, a new language for reality, a framework that holds both the smooth curves of space-time and the quantum jumps of particles in the same breath. When that framework emerges, and it won't replace Einstein or Bohr, it will honor them both, showing that each was right in their own domain and that the truth is wider than either imagined. For now, we stand at the edge. We hold two truths that refuse to touch. And in that tension and that impossibility, we find the spark that drives discovery forward. But there's another side to this story. Because even though our theories break at the Planck scale, the universe didn't break. It kept going. In that first unimaginable instant, when the cosmos was smaller than a grain of sand and hotter than any furnace, something happened. Forces unified, particles emerged, energy transformed. And though we can't describe it perfectly, we can trace its echoes. We can follow the thread forward from mystery to the world we know watching as the universe unfolds from chaos into order, from simplicity into the staggering complexity of stars, galaxies, and life itself. Imagine a moment so brief that light itself can't cross the width of a proton, a moment when the universe was so hot that atoms couldn't exist, molecules couldn't form, and even the fundamental particles we know today hadn't been born yet. A moment when all the matter and energy that would one day become galaxies, stars, planets, and you was compressed into a space smaller than the period at the end of this sentence. That moment was real. Physicists call it the Planck epoch, and it lasted exactly one Planck time. We've explored what the Planck scale means, the smallest distance, the briefest duration, the threshold where physics breaks down. Now we step into that threshold, not as observers with instruments because no instrument can reach there, but as storytellers following the thread of mathematics and inference backward to the very edge of existence, to the first tick of the cosmic clock, to a time when the universe was not yet the universe, but something stranger, hotter, denser, and more unified than anything we can directly imagine. The Planck epoch begins at time zero, if such a thing exists, and ends at roughly 10 to the negative 43 seconds after the Big Bang. In that incomprehensibly brief window, the universe underwent transformations so extreme that our everyday concepts of matter, energy, space, and time simply don't apply. The temperature during the Planck epoch is estimated to have been around 10 to the 32 Kelvin. To put that in perspective, the core of the sun is about 15 million Kelvin. The hottest temperature ever achieved in a laboratory in a particle collider is around 5 trillion Kelvin. The Planck temperature is 10 billion times hotter than that. At this temperature, energy is so concentrated that it becomes indistinguishable from matter and matter from force. In fact, during the Planck epoch, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were not separate. They were unified into a single primordial force. Physicists call this the grand unified force, though no one knows exactly what it looked like or how it behaved, because we have no theory that fully describes it. What we do know is that the symmetry was perfect. There were no distinctions, no hierarchies. Gravity was as strong as electromagnetism. The forces that hold atomic nuclei together were the same as the forces that would later govern the expansion of space itself. This symmetry didn't last. Symmetry never does. As the universe expanded and cooled, though cooled is almost a joke, when we're talking about temperatures that would vaporize anything instantly, the forces began to separate. First, gravity split off, becoming distinct from the other three forces. This probably happened at the end of the Planck epoch, though the exact moment is hidden in the fog of quantum uncertainty. Then, as the universe continued to cool, the strong nuclear force separated. Later, still the electromagnetic and weak forces split. By the time the universe was a trillionth of a second old, all four forces were distinct, each with its own character, its own strength, its own rules. But during the Planck epoch, none of that had happened yet. The universe was simpler then. Not easier to understand simplicity at that scale is almost incomprehensible but unified. One force, one field, one seething, roiling ocean of energy with no particles, no structure, no form. And yet, within that formless chaos, the seeds of everything were already present. Tiny quantum fluctuations, random ripples in the energy field, would later be stretched by cosmic inflation into the density variations that became galaxies. The laws of physics, though unified, were already written into the mathematics of existence, waiting to unfold as the temperature dropped and symmetry broke. It's worth pausing here to think about what hot means at this scale. We usually think of heat as the motion of particles, atoms, and molecules jiggling, vibrating, bouncing off each other. The faster they move, the hotter the substance. But during the Planck epoch, there were no atoms, no molecules, no particles as we know them. Quarks, the building blocks of protons and neutrons, couldn't exist yet because the temperature was too high. Electrons couldn't exist. Photons, the particles of light, couldn't exist in any stable form. What existed instead was a kind of primordial plasma, a state of matter or pre-matter that physicists sometimes call a quark-gluon plasma. Though even that term is misleading because it implies more structure than actually existed. At Planck, temperature's energy itself was the only reality. Pure, undifferentiated energy fluctuating wildly, governed by quantum uncertainty and the nascent laws of a universe still learning how to be. Think of it like this. If you heat ice, it melts into water. Heat it more, it boils into steam. Heat it even more, the water molecules break apart into hydrogen and oxygen. Keep heating, and the atom's ionized electrons rip away, leaving a plasma of charged particles. This is what happens inside stars, but go hotter still. Hot enough, and even atomic nuclei break apart. Protons and neutrons dissolve into quarks and gluons. And if you could go hotter than that, hotter than anything in the universe today, except perhaps the cores of colliding neutron stars, you'd reach a state where even quarks lose their identity. You'd reach the Planck epoch where matter is a word without meaning and only energy remains. Here's where it gets strange. During the Planck epoch, the density of the universe was approximately 10 to the 93 grams per cubic centimeter. A single cubic centimeter, about the size of a sugar cube, would have weighed more than all the stars in the observable universe combined. Space itself was so tightly curved by this density that it might not have been space in any sense we'd recognize. Some models suggest that space-time was quantized, made of discrete loops or strings, rather than a smooth continuum. Others propose that space and time were so entangled at this scale that they couldn't be separated into distinct dimensions. Time might have been more like space, and space more like time, in a kind of fuzzy, indeterminate state that defies description. And yet, despite this density, despite this heat, despite this chaos, the universe didn't collapse into a black hole. Why not? According to general relativity, concentrating that much mass energy into such a small volume should create an event horizon, a point of no return where gravity becomes inescapable. But general relativity doesn't work at the Planck scale. Quantum mechanics intervenes, though we don't fully understand how. Some cosmologists suggest that quantum effects create a kind of pressure, a resistance to further collapse that prevents a singularity from forming. Others propose that the Big Bang wasn't an explosion outward from a point, but a transition from a previous state, perhaps a contracting universe that bounced back, or a quantum fluctuation that tunneled from nothing into something. We don't know. And that uncertainty is not a flaw in science, it's a sign of honesty. The Planck epoch is beyond the reach of our current theories. We can extrapolate in for guess, but we cannot observe it directly. No telescope will ever see it because light itself didn't exist in a form we'd recognize. The cosmic microwave background, the oldest light in the universe, shows us the cosmos at 380,000 years old. Ancient, yes, but an eternity compared to the Planck epoch. To see the Planck epoch, we'd need to probe energies and time scales that are fundamentally inaccessible. But here's what we can do. We can follow the physics forward from that moment. We know what happened after the Planck epoch because the evidence is everywhere. After gravity separated from the other forces, the universe entered what's called the Grand Unification Epoch, where the strong, weak, and electromagnetic forces remained unified. This lasted until about 10 to the negative 36 seconds. Then the strong force split off, and the universe underwent a phase of exponential expansion called cosmic inflation. In less than a billionth of a second, the universe doubled in size at least 60 times, growing from subatomic to macroscopic in the blink of an eye, or faster, since light couldn't keep up. Inflation smoothed out the universe, stretching any initial irregularities into the nearly uniform cosmos we see today. But it didn't erase the quantum fluctuations. It amplified them, turning microscopic ripples in the energy field into cosmic scale variations in density. These variations became the seeds of structure, the slight overdensities where gravity would later pull matter together to form the first stars, the first galaxies, the filaments and voids that make up the cosmic web. After inflation, the universe continued expanding and cooling, but more slowly. At about 10 to the negative 12 seconds, the weak and electromagnetic forces separated. At around 10 to the negative 6 seconds, 1 microsecond, the universe cooled enough for quarks to bind together into protons and neutrons. This is called the quark epoch, and it marked the first time matter, as we'd recognize it, began to exist. Before this, there were no protons, no neutrons, no atomic nuclei, just quarks swimming in a sea of gluons, the particles that carry the strong force. By 1 second after the Big Bang, the universe had cooled to about 10 billion Kelvin. Still unimaginably hot, but cool enough for nuclear reactions to begin. Protons and neutrons fused into the lightest atomic nuclei, mostly hydrogen, some helium traces of lithium. This process, called Big Bang nucleosynthesis, lasted for about 3 minutes. By the time it ended, the universe was filled with a hot plasma of nuclei and electrons, but no atoms yet. Atoms wouldn't form for another 380,000 years, when the universe cooled enough for electrons to settle into orbits around nuclei, without being immediately knocked free by radiation. But all of this inflation nucleosynthesis, the formation of atoms and stars and galaxies, all of it traces back to the Planck epoch. That first moment set the initial conditions. The amount of energy, the balance of forces, the quantum fluctuations that would become galaxies, all determined in that first incomprehensible instant. Does that make you feel small, or does it make you feel connected? Every atom in your body was forged in the heart of a star. Yes, but the elements those stars fused trace back to the primordial hydrogen and helium created in the first 3 minutes. And that hydrogen, those protons, trace back to the quark epoch. And the quarks trace back to the unified force of the Planck epoch. You are in a very literal sense made of the Big Bang. You are a piece of that first moment cooled and condensed and rearranged into the shape of a person who can wonder about where they came from. Think about the improbability of it all. If the forces had separated differently, if gravity had been slightly stronger, or electromagnetism slightly weaker, stars might never have formed. If the quantum fluctuations during inflation had been a little larger, the universe would have collapsed into black holes. A little smaller, and no galaxies would have formed, no stars, no planets, no life. The Planck epoch set the dials, and somehow by chance or design or necessity, they were set just right. Cosmologists call this fine-tuning, and it's one of the deepest mysteries in physics. Why is the universe the way it is? Why these forces, these constants, this balance? Some say it's the anthropic principle we observe this universe because it's the only kind we could exist in. Others propose a multiverse, an infinite ensemble of universes with every possible combination of laws. And we just happen to live in one that allows complexity. Still, others suggest there's a deeper principle we haven't discovered, yet some underlying reason why the laws had to be this way. We don't know, and maybe we never will. But the question itself is beautiful. It reminds us that existence is not inevitable. The universe didn't have to be, and yet it is. And for one Planck time in that first fiery instant, everything hung in balance. Potential and actuality, being and nothingness. And then the balance tipped and existence won. The Planck epoch is the closest we can come to the moment of creation. Not creation in a religious sense, though some find spiritual meaning in it, but creation in the sense of transition from non-being to being, from no thing to something. It's the threshold moment. And what's remarkable is that we can know anything about it at all. We weren't there. No one was. No structure existed that could record it. And yet, through mathematics, through inference, through the patient work of generations of physicists, we can trace the universe's history back to that first incomprehensible instant. There's a humility in that, and a triumph. We are beings of flesh and thought, living 13.8 billion years after the beginning, and we can still touch it. We can still reach back across the eons and say this is where it started. This is the moment when time began to tick, when space began to expand, when the laws of nature crystallized from the formless potential of a unified field. And in that moment, everything you see around you was already there, compressed into a volume smaller than an atom. The stars, the planets, the oceans, the trees, the light in your eyes, all of it waiting to unfold. But the story doesn't end at the Planck epoch. It begins there. Because once the forces separated, once the universe started cooling, the real work of creation began. Not just particles, but structure. Not just energy, but complexity. The universe didn't just expand, it evolved. And the question we carry forward is whether that evolution was random, inevitable, or guided by principles we've only begun to glimpse. What if the Big Bang wasn't the beginning at all? What if the moment we've been calling the start of everything was actually a transition, a doorway rather than a foundation? What if time didn't begin, but transformed, and the universe we know emerged from something even stranger that we haven't yet found words to describe? These aren't idle questions. They're at the heart of modern cosmology, dividing some of the brightest minds in physics into competing camps, each with compelling evidence, elegant mathematics, and profound implications for what it means to exist. The classical picture of the Big Bang is clean and dramatic. At time zero, there was a singularity, a point of infinite density and infinite curvature where all the matter and energy in the universe was compressed into zero volume. Then, suddenly, expansion. Space itself began stretching, carrying galaxies apart like raisins in rising bread dough. This model, developed in the 1920s and refined over decades, explains so much. It predicts the expansion of the universe confirmed by Edwin Hubble in 1929. It predicts the cosmic microwave background discovered accidentally by Arno Penzias and Robert Wilson in 1965. It predicts the abundance of light elements, hydrogen, helium, lithium, created in the first few minutes ratios that match observations precisely. The Big Bang Theory is one of the great triumphs of 20th century science. But it has a problem, a deep, unsettling problem, the singularity itself. In 1970, Stephen Hawking and Roger Penrose published a proof that became one of the most important results in theoretical physics. Using the equations of general relativity, they showed that if the universe is expanding, and if general relativity is correct, then tracing the expansion backward inevitably leads to a singularity. Not probably, not maybe, inevitably. The math is airtight. If you run the cosmic movie in reverse, watching galaxies rush together, space contract, and temperature rise, you eventually reach a point where density becomes infinite and space-time curvature becomes infinite. Physicists hate infinities. Infinity in an equation is usually a sign that the equation has broken down, that you've pushed the theory beyond its domain of validity. When you calculate the gravitational force between 2-point masses and let the distance go to 0, Newton's equation gives you infinity. But real objects aren't points, they have size, so the infinity never happens in nature. It's a mathematical artifact. The singularity at the beginning of the Big Bang seems different. It's not an artifact of sloppy modeling. It's a prediction of the best theory of gravity we have. And yet most physicists believe it's not real. Not because they want to disbelieve it, but because general relativity itself tells us it's incomplete. At the Planck scale, quantum mechanics becomes essential. And general relativity doesn't include quantum effects. The singularity is a sign that we're missing something, that a deeper theory is needed. So, what replaces the singularity? What happens when you apply quantum mechanics to the Big Bang? Several proposals have emerged, each offering a different answer to the question of whether the universe began or emerged. One of the most influential is the Hartley-Hawking no-boundary proposal developed by James Hartle and Stephen Hawking in 1983. Their idea is subtle and mathematically sophisticated, but the core intuition is beautiful. They suggest that asking what came before the Big Bang is like asking what's north of the North Pole. The question assumes a direction that doesn't exist. At the North Pole, every direction is south. There is no north. Similarly, at the Big Bang, according to Hartley and Hawking, there is no before. Time doesn't extend backward past that point, not because something blocked it, but because time itself is finite in the past direction. To make this work mathematically, they use a trick called imaginary time. In ordinary time, we move forward at 1 second per second, ticking along a timeline. But in quantum mechanics, time can sometimes be treated as an imaginary number, a mathematical concept involving the square root of -1. When Hawking and Hartley applied this to the universe's wave function, they found that the Big Bang singularity smooths out. Instead of a sharp beginning, the universe has a kind of rounded edge like the south pole of a sphere. You can travel around it, but you never hit an edge or a boundary. The universe is finite but unbounded. It's a profound idea, but it's also controversial. Imaginary time is a mathematical tool, and it's not clear what it means physically. Does time really become space-like near the Big Bang? Or is this just a convenient way to avoid the singularity in the equations? Hawking himself admitted that the no-boundary proposal raises as many questions as it answers. But it does one thing beautifully. It eliminates the need for a beginning. The universe simply is eternally in a sense, even though it has finite age when measured in ordinary time. Another approach comes from loop quantum cosmology, an application of loop quantum gravity to the universe as a whole. In this framework, space is not continuous, but made of discrete quantum loops. When you apply this to the Big Bang, something remarkable happens. The singularity disappears. Instead of density becoming infinite as you go back in time, it reaches a maximum value extremely high, about the Planck density, but finite. And when density reaches this maximum, instead of collapsing further, the universe bounces back. The Big Bang becomes a big bounce. In this picture, our universe is not the first. Before the Big Bang, there was a previous universe contracting under its own gravity. It shrank and shrank until quantum effects kicked in, creating a kind of quantum pressure that halted the collapse and reversed it. The contraction became expansion. The Big Crunch became the Big Bang. And this might not be unique. Perhaps the universe has been bouncing forever, cycling through endless expansions and contractions, with our current epoch just one chapter in an infinite story. Loop quantum cosmology is appealing because it's based on a theory, loop quantum gravity, that tries to quantize space-time itself. It doesn't require extra dimensions or exotic particles. It just applies quantum mechanics to the geometry of space. And it makes predictions that could in principle be tested by looking at the cosmic microwave background for subtle patterns that might reveal quantum structure in the early universe. But there's a challenge. If the universe bounced, what happened to the information from the previous cycle? Was it erased, scrambled, preserved? And if there were infinitely many bounces, how do we explain the low entropy of our universe? Entropy, the measure of disorder, tends to increase over time. If the universe has been bouncing forever, entropy should be near maximum by now, and the universe should be a featureless, lukewarm soup. But it's not. It's full of structure galaxies, stars, life. This is called the entropy problem, and it's a serious objection to cyclic models. Roger Penrose, who proved the singularity theorem with Hawking, later proposed his own cyclic model to address this. He calls it conformal cyclic cosmology, or CCC. Penrose's idea is audacious. He suggests that after the universe reaches its ultimate fate, a cold, dark, empty void, filled only with radiation and scattered particles, everything spreads so thin that nothing interesting will ever happen again. It doesn't just end. Instead, it transforms. In the far future, when all matter has decayed and only massless particles remain, the distinction between space and time becomes meaningless. The universe, in a sense, forgets its size, and this far future state becomes indistinguishable from the conditions at the Big Bang of a new universe. Penrose proposes that the end of one eon is the beginning of the next. The heat death of our universe is the Big Bang of another. Time doesn't cycle in the usual sense. It's more like a spiral, each aeon building on the ghost of the last. And Penrose claims to have found evidence for this in the cosmic microwave background. He and his collaborators have pointed to certain circular patterns in the CMB that they interpret as the imprint of catastrophic events colliding black holes from a previous aeon. Most cosmologists are skeptical of these claims, but they're intriguing enough to warrant further investigation. Then there's eternal inflation, an idea that comes from a different direction entirely. Alan Guth introduced cosmic inflation in 1980 to solve several problems with the standard Big Bang model. Inflation proposes that in the first tiny fraction of a second, the universe underwent exponential expansion, growing from subatomic to macroscopic in less time than it takes light to cross an atom. This expansion smoothed out initial irregularities, explaining why the universe looks so uniform on large scales. But Andre Linde and others realized that if inflation can start, it might never completely stop. In most of space, inflation ends, and the universe settles into the slower expansion we observe today. But in some regions, quantum fluctuations keep inflation going. Those regions expand exponentially, creating more space. And within that space, more fluctuations, more pockets where inflation continues. This process goes on forever, creating an infinite multiverse, a vast cosmic landscape of bubble universes, each with potentially different physical laws, different constants, different outcomes. In eternal inflation, the Big Bang wasn't the beginning of everything. It was the beginning of our bubble, our pocket universe. But the process that created it has been running forever and will continue forever. There was no first moment, no initial cause, just an eternal self-sustaining field of inflation, spawning universes the way a tree drops seeds. This model solves some problems, but creates others. If there are infinitely many universes, each with different properties, then the fact that our universe has the right conditions for life is no longer surprising. It's just selection bias. We exist in the kind of universe that allows observers to exist. But this also makes prediction nearly impossible. If anything that can happen does happen somewhere in the multiverse, then what does the theory actually predict? Some physicists see this as a strength, a framework so vast it encompasses all possibilities. Others see it as a weakness, a theory that explains everything by explaining nothing. And then there are models that suggest the Big Bang emerged from quantum fluctuations in a pre-existing space. Imagine a field perfectly uniform, sitting in its lowest energy state, what physicists call the vacuum. In quantum mechanics, even the vacuum isn't perfectly still. It fluctuates. And occasionally, by pure chance, a fluctuation large enough to create a universe occurs. This is how Alexander Vilenkin describes it. The universe tunneled into existence from nothing, borrowing energy from the gravitational field. which has negative energy that can balance the positive energy of matter and radiation. This sounds bizarre, but it's mathematically consistent, and it's testable, at least in principle. If the universe began from a quantum tunneling event, there should be specific signatures in the distribution of galaxies and the properties of the cosmic microwave background. So far, we haven't seen them, but we keep looking. What's striking about all these models, no boundary big, bounce, conformal, cyclic cosmology, eternal inflation, quantum tunneling, is that none of them require a singularity. They all propose that the Big Bang, as we observe it, was not the ultimate beginning, but a transition, an emergence, a phase change. The universe didn't start from nothing. It started from something else, something quantum, something without time as we know it, something that defies easy description because we don't have the physics to describe it yet. And this brings us to a deeper question. What does beginning even mean? We think we know. Beginning is when something starts when it wasn't there before, and then it is. But that definition assumes time. It assumes a before and an after. At the Big Bang, if time itself began, then before has no meaning. And if time didn't begin but transformed, then the Big Bang is not a beginning. It's a boundary, a transition, a moment of radical change, but not creation from absolute nothingness. Does this bother you? It should. Not because it's wrong, but because it challenges our intuition. We are creatures who live in time. We experience birth and death, cause and effect, memory and anticipation. We can't help but think of the universe in the same terms. But the universe is under no obligation to match our intuition. It simply is what it is. And if what it is includes a timeless quantum state from which time emerges, or an eternal cycle of creation and destruction, or an infinite multiverse of bubbles, then so be it. Our job is to follow the evidence, not our preferences. Here's the honest truth we don't know yet. We have multiple models, each mathematically rigorous, each with strengths and weaknesses. Some can be tested, others may remain beyond the reach of observation. And it's possible that the question itself, did the Big Bang begin or emerge, is too simplistic. Maybe the answer is both, or neither, or something we haven't imagined yet. But the question matters, because how the universe began shapes everything that came after. It determines why there's something rather than nothing, why the laws of physics are what they are, why the universe is structured the way it is. And it touches on the most profound mystery of all: why does existence exist? We stand now at the crossroads of observation and speculation, of data and imagination. The cosmic microwave background whispers secrets from 380,000 years after the Big Bang. Gravitational waves might one day carry messages from even earlier, from the moment of inflation itself. And future experiments probing quantum gravity might finally reveal what happens at the Planck scale. When they do, we'll know whether the Big Bang was a beginning and emergence or something altogether stranger. But even now, in this uncertainty, there's beauty. Because the universe has given us a gift, the ability to ask, to wonder, to build telescopes and equations and models, to stand beneath the stars and trace our lineage back to the first moment of heat and light, and to know that the answer when it comes will be more astonishing than anything we could have invented on our own. What we do know is this: whether it began or emerged, the universe became. And in becoming, it created space for galaxies, for stars, for planets, for life, for you. And that becoming is still happening, still unfolding, still carrying forward the echo of that first impossible moment when everything changed. From these competing visions of creation, we turn now to something even stranger. Because if the Planck scale is the smallest distance, and if space at that scale is not smooth but foaming, bubbling, churning with quantum chaos, then what we call empty space might be the least empty thing in existence. Empty space isn't empty. If you could zoom in far enough past atoms, past quarks, past the Planck length itself, you'd find that the smooth fabric of reality we take for granted is actually seething, bubbling, churning, like the surface of a pot about to boil. Space at its deepest level is alive with quantum chaos. Physicists call it quantum foam. And it might be the strangest thing in the universe. This is where the abstract becomes visceral, where mathematics stops being numbers on a page and starts painting a picture so bizarre, so fundamentally weird, that even the scientists who study it admit they can't fully visualize it, but they can describe it. And what they describe is a reality where nothing stays still, where particles flash in and out of existence, where the vacuum is less like emptiness and more like a storm seen from very far away. The idea of quantum foam was introduced by John Archibald Wheeler in 1955. Wheeler was one of the great visionaries of 20th century physics, a mentor to Richard Feynman, and a collaborator with Niels Bohr. He had a gift for finding simple words for complex ideas. He coined the term black hole in 1967, replacing the awkward phrase gravitationally collapsed object. He popularized the idea of it from bit, suggesting that information is more fundamental than matter. And he gave us quantum foam, a metaphor so vivid that it stuck for nearly 70 years. Wheeler's insight came from thinking about quantum mechanics at the smallest possible scales. In quantum mechanics, uncertainty is fundamental. You can't know both the position and momentum of a particle with perfect precision. The more accurately you measure one, the less you can know about the other. This isn't a limitation of instruments, it's built into the fabric of reality. Particles don't have definite positions until you measure them. They exist as probabilities smeared across space in what's called a wave function. Now, apply this idea to space itself. At ordinary scales, space looks smooth, continuous, geometric. You can draw a line, measure a distance mark, a point. But at the Planck scale, uncertainty takes over. Space doesn't have a definite shape. It fluctuates. And if space fluctuates, then space-time, the unified fabric of space and time, must be fluctuating too. It ripples, bends, twists, and even tears all on time scales, so brief in length scales so small that we can't observe it directly. But the mathematics says it's there. Imagine you're looking at the ocean from an airplane. From high up, the surface looks smooth, almost glassy. You can see the coastline, the color gradients, maybe a few boats. But as you descend, details emerge. What looks smooth becomes wavy. Closer still, and you see white caps, foam, spray. At sea level, the ocean is turbulent, constantly in motion, never the same from one moment to the next. That's what space is like at the Planck scale. From our vantage point, enormous. Compared to a Planck-length space, looks calm. But zoom in and it's chaos. Wheeler described this chaos as foam because the fluctuations aren't random noise. They have structure. At the Planck scale, quantum uncertainty is so strong that space itself might break apart into tiny temporary wormholes, tunnels connecting different parts of space-time. These wormholes would appear and disappear in less than Planck time 10 to the negative 43 seconds. They'd be smaller than a Planck length 10 to the negative 35 meters. You couldn't see them, couldn't measure them, couldn't send anything through them. But they'd be real, constantly forming and dissolving, giving space-time a frothy, foamy texture. This isn't science fiction. It's a consequence of taking quantum mechanics seriously and applying it to gravity and space-time. If particles can fluctuate, why not space? If energy can appear and disappear in the form of virtual particles, why not geometry? The equations allow it. In fact, they seem to demand it. Let's talk about virtual particles for a moment because they're key to understanding quantum foam. In classical physics, empty space is just that, empty. A perfect vacuum contains nothing. But in quantum field theory, which combines quantum mechanics with special relativity, the vacuum is teeming with activity. Particle-antiparticle pairs constantly pop into existence, borrowed from the vacuum's energy, and then annihilate each other almost instantly, paying the energy back before the universe notices the debt. These are called virtual particles, and they're not just theoretical. They have measurable effects. One of the most famous is the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948. Casimir wondered what would happen if you placed two uncharged metal plates very close together in a vacuum. According to classical physics, nothing should happen. There's no force between them, no charge, no magnetism. But quantum mechanics says otherwise. The vacuum between the plates is filled with virtual photons, particles of light that flash in and out of existence. However, the space between the plates is so narrow that only virtual photons with certain wavelengths can fit. Outside the plates, all wavelengths are possible. This creates an imbalance, a tiny pressure difference, and the plates are pushed together. In 1997, physicist Steve Lamoureux measured the Casimir effect with incredible precision, and it matched the predictions exactly. The vacuum isn't empty. It's fizzing with virtual particles, and that fizzing exerts real measurable force. If virtual particles are real, then the quantum foam they emerge from must be real too. But here's where it gets stranger. Virtual particles don't just appear in pairs. They borrow energy from the vacuum, and according to Heisenberg's uncertainty principle, they can exist as long as they don't violate energy conservation for too long. The more energy they borrow, the shorter their lifespan. A virtual electron-positron pair might last for about 10 to the negative 21 seconds. A virtual quark-antiquark pair might last even less. But during that brief existence, they're as real as anything else. They interact with other particles. They contribute to the properties of atoms and molecules. In a sense, the vacuum is not the absence of stuff, it's the presence of potential. Now scale this down to the Planck level. At this scale, the energy fluctuations are enormous. We're not talking about electron-positron pairs. We're talking about fluctuations so energetic that they could briefly create black holes. Tiny microscopic black holes, each one existing for about 1 Planck time before evaporating via Hawking radiation. These are called quantum black holes, and they're part of the foam. They form, evaporate, and leave behind ripples in space-time that affect other fluctuations. It's a self-feeding process, a kind of quantum turbulence where energy and geometry dance together in patterns too complex to fully calculate. John Wheeler once said that quantum foam is where the game gets played. At ordinary scales, space is the stage on which events unfold. But at the Planck scale, space itself is an event. It's not a container, it's a participant. And this has profound implications for what we mean by existence. Think about what a point in space is. We usually imagine it as a location, a set of coordinates, something definite. But if space is foaming, then points don't stay put. They smear out into probabilities. The very idea of here becomes fuzzy. And if here is fuzzy, then so is now. Because space and time are linked in space-time. The quantum foam doesn't just affect space, it affects time too. At the Planck scale, time might not flow smoothly. It might stutter, branch loop back on itself. Cause and effect, which we take for granted at macroscopic scales, might break down entirely. This is not idle speculation. Some versions of quantum gravity, like loop quantum gravity, explicitly predict that space-time is made of discrete chunks quanta of space and time woven together like a fabric. In this picture, the Planck scale is not where space becomes foamy. It's where space becomes visible as something made of parts, like zooming in on a digital photograph until you see the individual pixels. The foam is the texture of those pixels, the quantum noise that comes from their interactions. String theory offers a different picture. In string theory, particles aren't points, but tiny vibrating strings. And the way a string vibrates determines what kind of particle it is. Space in string theory is smooth even at the Planck scale, but it's filled with vibrating strings. And those vibrations create a kind of harmonic foam. The strings don't just sit in space, they define it. Space is the emergent property of their collective vibrations. It's a bit like sound waves in air. The air molecules are discrete, but the sound is continuous, emerging from their coordinated motion. Both approaches loop quantum gravity, and string theory agree that the Planck scale is where space stops being what we think it is. But they disagree on the details, and so far, we have no way to test which, if either, is correct. The The Planck scale is beyond the reach of any experiment we can currently imagine. To probe it directly, you'd need energy so high that the particle accelerator would have to be larger than the solar system. And even if you could build it, concentrating that much energy into such a small space would create a black hole, destroying the very thing you're trying to study. So, how do we know quantum foam is real? We don't, not directly, but we can infer it. The vacuum has measurable energy, something we call vacuum energy or zero-point energy. Even at absolute zero, when all thermal motion has stopped, quantum fields still fluctuate. Those fluctuations have energy, and that energy contributes to the cosmological constant, the mysterious force driving the accelerated expansion of the universe. We call it dark energy, and it makes up about 68% of the total energy content of the cosmos. If the vacuum weren't foamy, if it were truly empty, dark energy wouldn't exist. There's also evidence from particle physics. When physicists calculate the properties of particles, their masses, their magnetic moments, their interaction probabilities, they have to account for virtual particles. An electron, for example, is constantly surrounded by a cloud of virtual photons and virtual electron-positron pairs. These virtual particles shield the electron's charge, making it look slightly weaker than it actually is at very close distances. This effect, called charge screening, has been measured, and the measurements match the predictions to extraordinary precision. The quantum foam is not just a metaphor, it's a measurable reality. But here's the puzzle. When physicists try to calculate how much vacuum energy there should be based on quantum field theory, they get an answer that's about 120 orders of magnitude too large. That's a 1 followed by 120 zeros. It's the worst prediction in the history of science. If the vacuum energy were actually that large, the universe would have blown apart in the first instant of its existence. Clearly, something is wrong. Either there's a mechanism we don't understand that cancels out most of the vacuum energy, or our understanding of quantum foam is incomplete. This is called the cosmological constant problem, and it's one of the deepest unsolved mysteries in physics. It suggests that something fundamental is missing from our theories. Maybe space isn't what we think it is. Maybe the foam isn't foam at all, but something more structured, more subtle, governed by laws we haven't discovered yet. And yet, despite this mystery, the concept of quantum foam has been incredibly useful. It's changed the way physicists think about space-time and the vacuum. It's led to predictions about black hole entropy, about the holographic principle, about the ultimate limits of computation and information storage. It's shown that the universe at its deepest level is far stranger than the smooth, deterministic clockwork that Newton imagined. It's a universe where nothing is truly stable, where even the void trembles with possibility. Have you ever felt that the world is more fragile than it seems? That beneath the solid ground, beneath the certainty of objects and distances, there's something trembling, something uncertain. That's not just a feeling, that's physics. At the Planck scale, the ground does tremble. Space itself is not a foundation. It's a process, a constant negotiation between energy and geometry, between being and becoming. And this has philosophical implications. If space is not a fixed stage, but a fluctuating field, then what does that say about reality? Are we patterns in the foam, temporary structures that emerge from quantum chaos and will one day dissolve back into it? Or are we something more, something that transcends the foam, even as we're built from it? These aren't questions physics can answer alone, but physics gives us the language to ask them properly, and that language tells us that the universe is not made of things. It's made of interactions, relationships, probabilities. The quantum foam is the purest expression of this. It's where the universe is most itself, most alive, most quantum. There's a beauty in that, a kind of cosmic democracy. At the Planck scale, everything is equal. Particles and forces, space and time, existence and non-existence, all of it fluctuating together in the foam, none of it privileged, none of it permanent. It's the ultimate egalitarian reality where even the vacuum gets to participate, where even nothingness has structure and energy and life. John Wheeler, who gave us the idea of quantum foam, also said something else that's worth remembering. He said the universe is participatory. It doesn't exist independently of observation. The act of measuring, of asking questions, of probing with experiments collapses wave functions and brings possibilities into actuality. In a very real sense, we create the universe by observing it. Not in a mystical way, but in a quantum mechanical way. The foam is there always, but what we find in it depends on how we look. And so, the Planck scale, the realm of quantum foam, is not just the smallest distance. It's the place where physics meets philosophy, where science meets wonder, where the question, what is real, finds its deepest, strangest answer. Real is what interacts. Real is what fluctuates. Real is the foam itself churning endlessly, giving birth to space, to time, to particles to us. But if space is foam and the foam is all there is, then where did it come from? Did the foam always exist bubbling away for eternity? Or was there a moment when even the foam had to be born? This brings us back, as it always does, to the question of beginnings. And to the most haunting question of all, what if anything came before? What came before the Big Bang? It's the most natural question in the world. Children ask it. Philosophers have pondered it for millennia. And physicists, despite all their equations and observations, still struggle to answer it. Not because they lack intelligence or data, but because the question itself might be built on a faulty assumption. The assumption that before has meaning. This is where science reaches its most profound limit. Not a failure, but a boundary. A place where the tools of physics meet questions that may lie beyond physics itself. And in that meeting, we discover something surprising, that mystery is not the enemy of knowledge. It's the texture of it. The question, what came before the Big Bang, feels obvious. We live in time. Every event has a cause. Every beginning has something that came before it. You were born, but before that, your parents existed. The Earth formed, but before that, the solar nebula swirled in space. The sun ignited, but before that, a molecular cloud collapsed under gravity. Everything has a precursor, a prior state, a history that extends backward. So surely the Big Bang must too. But here's the problem. Time as we understand it is not a backdrop. It's not a river that was always flowing waiting for the universe to jump in. Time is part of the universe. It's woven into the fabric of space-time, inseparable from space itself. When the universe began, time began. And if time began at the Big Bang, then there is no before. The question dissolves not into an answer, but into a realization that the question was shaped by a framework that doesn't apply. This idea is not new. Saint Augustine of Hippo grappled with it in the 4th century. People would ask him mockingly, what was God doing before he created the universe? Augustine's response was brilliant. He said there was no before. Time itself was created with the universe. Before creation, there was no time. So the word before has no referent. It's a grammatical illusion, a question that sounds meaningful but isn't. Augustine didn't have general relativity or quantum mechanics, but his intuition was correct. Time is not eternal, it's contingent. In the 20th century, Einstein gave this idea mathematical teeth. His general theory of relativity showed that time and space are not separate. They're dimensions of a single entity space-time, and that entity can bend, stretch, and even begin. If space-time began at the Big Bang, then asking what came before is like asking what's north of the North Pole. It's a category error. North is a direction defined within the framework of Earth's geometry. Once you reach the pole, the concept stops working. Similarly, before is a direction in time. Once you reach the beginning of time, the concept stops working. But not everyone is satisfied with this answer. It feels like a dodge, a semantic trick to avoid a hard question. And so, physicists have proposed alternatives models where before does have meaning, where the Big Bang is not a beginning, but a transition, and where something, perhaps something very strange, came before. One of the most elegant is the idea of a cyclic universe, which we touched on earlier. In this model, the universe doesn't have a single beginning. It oscillates, expanding and contracting in endless cycles. The Big Bang was the moment of maximum contraction in one cycle, followed by expansion. Eventually, the expansion slows reverses, and the universe collapses back into another big crunch, which becomes the next Big Bang. Before our Big Bang, there was a previous universe. Before that, another. And so, on infinitely into the past. Roger Penrose's conformal cyclic cosmology is a version of this idea, but with a twist. Penrose suggests that the far future of one universe after all matter has decayed, and only massless radiation remains is mathematically identical to the hot, dense state at the beginning of the next universe. The end becomes the beginning. Time doesn't cycle in a circle, but spirals forward each aeon building on the remnant of the last. In this model, before the Big Bang is not empty nothingness. It's the heat death of a previous cosmos, a state so dilute and cold that it forgets its own size and reboots as a new Big Bang. Penrose even claims to have found evidence for this. He points to certain patterns in the cosmic microwave background, concentric circles of slightly higher temperature that he interprets as the remnants of violent events like black hole collisions from a previous aeon. Most cosmologists are skeptical. The patterns could be statistical flukes, artifacts of how we process the data. But the idea is tantalizing. If Penrose is right, then the universe is far older than 13.8 billion years. That number is just the age of the current aeon, one chapter in an eternal book. Another approach comes from loop quantum cosmology. In this framework, the Big Bang wasn't a singularity, but a big bounce. Before the Big Bang, the universe was contracting, shrinking under its own gravity. But instead of collapsing to infinite density, quantum effects kicked in at the Planck scale, creating a repulsive force that halted the collapse and reversed it. The contraction became expansion. The universe before the bounce was real, with galaxies, stars, perhaps even life. But all of that was erased, scrambled, compressed, and then re-expanded into the universe we see now. This is deeply unsettling. If loop quantum cosmology is correct, then there might have been civilizations before ours, entire histories, and all of it was wiped clean by the bounce. We would have no way of knowing. The information would be lost, or at best encoded in such distorted ways that we couldn't reconstruct it. The universe in this sense has amnesia. It remembers nothing before the bounce. Then there's eternal inflation, which we discussed earlier. In this model, our Big Bang was not the beginning of everything. It was the beginning of our bubble, our pocket universe within a much larger inflating space. That larger space has been inflating forever, spawning bubble universes endlessly. Before our Big Bang, other bubbles were forming, and before those others still. There is no first moment, no initial cause. Just an eternal process of creation driven by a quantum field that never fully settles. Eternal inflation sidesteps the question of absolute beginning by denying that there is one. The multiverse in this view is past eternal. It's always been inflating, always spawning universes, and always will be. Our Big Bang is just a local event important to us, but cosmically unremarkable. Time in the larger multiverse has no beginning. Only our local time, the time within our bubble, has a start. And then there's the most radical proposal of all creation from nothing. Not from empty space, but from true nothingness, no space, no time, no fields, no laws. This is the idea explored by cosmologists like Alexander Vilenkin and Lawrence Krauss. They argue that quantum mechanics allows for something to emerge from nothing, because in quantum mechanics, nothing is unstable. Here's how it works. In quantum field theory, even the vacuum, the lowest energy state, has fluctuations. These fluctuations can very rarely produce a universe. The universe starts as a tiny quantum fluctuation, a bubble of space-time that tunnels into existence. Once it exists, inflation takes over, blowing it up to macroscopic size. The energy needed to create the universe is borrowed from the gravitational field. which has negative energy that can cancel out the positive energy of matter and radiation. The total energy of the universe when you account for gravity might be exactly zero. You can get a universe from nothing, because in a sense the universe is nothing, just a rearrangement of zero. This sounds absurd, almost mystical. A universe from nothing. But it's mathematically rigorous. The equations allow it. And Vilenkin has argued that the probability of such a tunneling event, while incredibly small, is not zero. And if the probability is not zero, and you wait long enough, though waiting doesn't make sense without time, then eventually it happens. A universe sparks into being. But this raises a deeper question: what is nothing? Vilenkin and Krauss define it as the absence of space-time and matter. But they still assume the existence of quantum mechanics, of probabilistic laws of mathematics itself. Are those not something? If the laws of physics exist even in potential, then nothingness is not truly nothing. It's a kind of pre-physical state, a substrate of law and logic from which universes can emerge. Critics, including philosopher and physicist David Albert, have pointed this out. They argue that calling this nothing is misleading. True nothingness would be the absence of everything, including laws, but such a state is incoherent. We can't even think about it, let alone describe it with equations. So, when cosmologists say the universe came from nothing, they really mean it came from a quantum vacuum state, which is something just not something we'd recognize as stuff. And yet, even granting this criticism, the achievement is profound. Because what cosmologists have shown is that you don't need a pre-existing universe, a god, or an eternal substance to get a Big Bang. You just need the laws of quantum mechanics and general relativity. And those laws, far from being arbitrary, might be the only logically consistent framework that allows for stable, structured universes. In this view, the laws of physics are necessary truths, like the axioms of mathematics. They couldn't be otherwise. But this pushes the question back one more step. Why do those laws exist? Why is there quantum mechanics rather than something else or nothing at all? This is what philosophers call the ultimate question. Why is there something rather than nothing? And here physics falls silent. Not because physics has failed, but because the question lies beyond its domain. Physics explains how the universe behaves given certain laws. It cannot explain why those laws exist in the first place. Some physicists are comfortable with this. They see it as a natural boundary, a place where science hands the baton to philosophy or theology or personal reflection. Others keep pushing, proposing that the laws themselves might emerge from something deeper, perhaps a landscape of all possible laws, realized in different universes within a vast multiverse, with ours being just one possibility among infinite others. But this doesn't solve the problem. It just moves it. Why does the landscape exist? Why is there a multiverse rather than no multiverse? We seem to be stuck. Every answer raises another question. Every explanation requires something to be explained. It's turtles all the way down, as the old joke goes. Or is it? Maybe the problem is that we're asking the wrong kind of question. We're looking for a causal explanation, something that came before and caused the Big Bang. But causation requires time. And if time began at the Big Bang, then causation itself began. Asking for a cause of the Big Bang is asking for a temporal explanation of a non-temporal event. It's like asking what sound the color blue makes. The categories don't match. This doesn't mean there's no answer. It means the answer might not be a story. It might be a pattern, a principle, a mathematical necessity. The universe exists because it must in the same way. A triangle's angle must sum to 180 degrees in flat geometry. Not because something forced it to, but because the alternatives are logically incoherent. Physicist Max Tegmark has proposed this idea in its most radical form. He suggests that mathematics is not just a language we use to describe the universe. It is the universe. Every mathematically consistent structure exists, and our universe is one of them. We experience this particular structure because we are part of it, but countless other mathematical structures exist in parallel, each as real as ours. In this view, asking why the universe exists is like asking why the number 3 exists. It just does as a logical necessity. Tegmark's idea is controversial, even among physicists who love bold speculation. But it highlights a key insight. The question of ultimate origins might not have an answer in the traditional sense. We expect a narrative first, then the Big Bang. But reality doesn't owe us a narrative. It might just be. And our discomfort with that, our hunger for a story, might say more about us than about the universe. Augustine understood this. He said that time is a feature of the created world, not of the creator. Asking what God was doing before creation assumes God exists in time, but God, in Augustine's view, is outside time. Creation is the act that brings time into being. Modern cosmology has arrived at a similar structure, though without invoking a deity. The Big Bang is the event that brings time into being. Before the Big Bang, there is no before. Does this mean we should stop asking? Absolutely not. The question is beautiful precisely because it's unanswerable in the usual way. It forces us to think about the limits of thought, the boundaries of explanation, the nature of existence itself. And in doing so, it reveals something important, that wonder is not a gap to be filled, but a space to be inhabited. There's a Zen koan that asks, what is the sound of one hand clapping? The question is not meant to be answered with a sound. It's meant to break the mind's habit of seeking simple answers, to open up a different way of seeing. What came before the Big Bang is like that. It's a question that points beyond itself to the mystery at the heart of being. And in that mystery, we find not confusion, but clarity. Because the universe doesn't need a before. It doesn't need a cause in the ordinary sense. It simply is. And the fact that it is, and that we are here to ask the question, is more astonishing than any answer we could imagine. So, we stand at the edge of knowledge, looking back toward the beginning. And we see that the beginning might not be a point in time, but a boundary in logic, a limit, where physics meets philosophy, and both point towards something ineffable. And that's not a failure, it's an invitation. An invitation to wonder, to question, to sit with uncertainty and find peace in it. Because the universe gave us minds capable of asking why, but it didn't promise we'd always get answers. And maybe that's the greatest gift of all. From this edge where questions dissolve into silence, we turn at last to gather what we've learned, to hold it gently, and to see how it changes the way we understand not just the cosmos, but ourselves within it. We've traveled together through the smallest distances the universe allows, through moments briefer than thought, through the places where physics breaks down and mystery takes over. We've stood at the threshold of existence itself, asking questions that might not have answers and finding beauty in the asking. Now, as we drift toward rest, let's gather what we found and hold it gently, like starlight caught in cupped hands. Did the Big Bang begin at the Planck scale? The honest answer is, we don't know for certain. But what we do know is extraordinary. We know that at 10 to the negative 35 meters and 10 to the negative 43 seconds, the universe reaches a boundary. Not a wall, but a threshold where our theories, general relativity and quantum mechanics, both point towards something neither can fully describe. We know that at those scales, space might be foamy, time might be grainy, and the very concepts we use to navigate reality start to shimmer and dissolve. We know that Max Planck, sitting at his desk in 1900, trying to solve a puzzle about heated objects and light, stumbled upon constants that would define the ultimate limits of measurement. He didn't set out to find the edge of the knowable universe. He just wanted his equations to work. But in making them work, he revealed something profound, that nature has a resolution, a pixel size beneath which the questions we ask stop making sense in the ways we expect them to. We know that the Planck epoch, that first incomprehensible instant when the universe was smaller than an atom and hotter than anything we can create, set the initial conditions for everything that came after. The forces were unified, the symmetry was perfect. And then as the universe expanded and cooled, that symmetry shattered like a crystal, dropped on stone, and the four fundamental forces separated, each taking on its own character, its own strength, its own role in shaping reality. We know that Einstein's equations, beautiful as they are, precise as they have proven to be, stumble at the Planck scale. They predict singularity's points of infinite density, which are almost certainly not real. They tell us that something is missing some piece of the puzzle we haven't found yet. And we know that quantum mechanics, despite its strangeness and its success, cannot describe gravity. The two great frameworks of 20th century physics stand like pillars of a bridge that was never completed, each supporting its own side, but not quite meeting in the middle. We know that physicists have proposed many ways to complete that bridge. String theory, with its vibrating loops and extra dimensions. Loop quantum gravity with its discrete chunks of space-time woven like fabric. Conformal cyclic cosmology with its eternal spiral of aeons. Eternal inflation with its endless multiverse of bubble universes. Quantum tunneling from nothing, where the universe borrows existence from the vacuum and never pays it back. Each theory is elegant in its own way. Each solves certain problems, and each remains untested at the scale where it would matter most. And we know this, that the question of whether the Big Bang began or emerged is not just a technical dispute about cosmology. It's a question about the nature of time, the meaning of existence, and the limits of human knowledge. It's a question that sits at the intersection of physics philosophy and something harder to name, something like awe. Think about how far we've come, not just in this conversation, but as a species. 500 years ago, we didn't know the Earth orbited the sun. We thought the cosmos was a set of crystal spheres, unchanging and eternal. 300 years ago, Newton gave us gravity as a force, but he had no idea what space and time really were. 100 years ago, Einstein revealed that space and time are woven together, that mass curve space-time, and that the universe itself might have a beginning. 50 years ago, Hawking and Penrose proved that beginning must have been a singularity, and Hawking later showed that black holes radiate, that quantum mechanics touches everything, even gravity. And now, here we are, barely a century after learning the universe had a beginning, asking not just what happened at that beginning, but whether beginning is even the right word. We've traced the history of everything back to the first microsecond, the first nanosecond, the first Planck time. We've touched the edge of creation with mathematics and inference, and though we cannot see it directly, we know it shaped us. Every atom in your body, every photon of light that's ever warmed your skin, every force that holds molecules together, all of it traces back to that first moment, whatever it was. Does that make you feel small? It should. Not in a diminishing way, but in a liberating one. Because smallness is not insignificance. You are small compared to galaxies, yes. But galaxies are not conscious. They do not wonder. They do not ask where they came from or what it all means. You do. And that capacity to question, to imagine, to reach with thought into realms no eye will ever see, that is what makes you vast. The Planck scale is the smallest stage, but the questions it raises are the largest we can ask. Why is there something rather than nothing? Why these laws and not others? Why does the universe seem fine-tuned for complexity, for stars, for life, for minds that can contemplate the Planck scale? We don't have final answers. We have hypotheses, models, ongoing debates. And that's exactly as it should be. Science is not a collection of answers. It's a process of asking better questions. And sometimes the best questions are the ones that humble us, the ones that remind us we are finite creatures in an infinite cosmos, or at least a cosmos so vast and old and strange that infinity is a reasonable approximation. We live for a few decades on a small planet orbiting an ordinary star in the suburbs of a typical galaxy, one of hundreds of billions in the observable universe. And yet, with telescopes and equations, with patience and creativity, we've looked back 13.8 billion years to the first light of creation. We've peered into black holes, detected gravitational waves, measured the curvature of space, and calculated the temperature of the Big Bang to extraordinary precision. That's not a small achievement. That's a miracle of the human mind. And it was accomplished not by knowing everything, but by being willing to admit what we don't know, and then working slowly, carefully, collaboratively to push the boundary of ignorance back just a little further. The Planck scale might remain forever beyond our direct observation. We might never build an experiment that probes 10 to the negative 35 meters. We might never watch a quantum foam bubble form and collapse. But we can infer it. We can model it. We can test predictions that follow from it. And slowly, piece by piece, we can construct a picture of what happened at the beginning, even if that picture is sketched in probabilities and approximations rather than certainties. And here's the thing, even if we someday achieve a theory of quantum gravity, even if we solve the Planck scale puzzle completely, there will still be mystery. There will still be questions. Because the universe is not a problem to be solved once and for all. It's a conversation that never ends each answer, opening up new questions, each discovery revealing new horizons. Some people find this frustrating. They want closure, finality, the last word. But I think there's a quiet joy in knowing that the conversation will outlast us. That future generations will ask questions we haven't imagined yet, using tools we can't envision. And they'll find answers that will astonish them as much as the Big Bang astonishes us. The search for understanding is not a burden, it's a gift. And it's one we pass forward each generation to the next, like a torch that never goes out. So, did the Big Bang begin at the Planck scale? Maybe, probably, in some sense. But the deeper truth is this: the universe began in mystery, it unfolds in mystery, and it will end if it ends in mystery. And we, improbable collections of atoms arranged by chance and necessity into forms capable of thought, get to witness it. We get to be the universe looking at itself, asking itself questions, marveling at itself. Carl Sagan once said, "We are a way for the cosmos to know itself." He was right. Every time you look up at the stars, every time you wonder about the Planck scale or the Big Bang or what came before you, or the universe becoming conscious of its own existence, you are 13.8 billion years of cosmic evolution concentrated into a single point of awareness. And that awareness, that capacity for wonder, is as much a part of the universe as black holes and quantum foam. There's a tendency, especially in science, to focus on what we don't know, on the gaps and the problems. But let's not forget what we do know. We know that the universe is comprehensible, that it follows laws, that those laws can be written in mathematics, and that we, fragile and fleeting as we are, can understand them. We know that the same forces that governed the Planck epoch still govern us today, just expressed differently, cooled and separated and complexified over billions of years. We know that we are connected to the beginning in the most literal way possible. We are made of it. And we know that knowledge is not the enemy of wonder, it's the midwife. The more we understand about the Planck scale, about quantum foam, about the Big Bang, the more astonishing it becomes. Not less. More. Because knowledge reveals layers we didn't know existed, complexities we couldn't have guessed, beauties hidden in the mathematics that governs reality. I hope as you drift towards sleep tonight, you carry some of that astonishment with you. I hope you feel the weight of 13.8 billion years in your bones, the heat of the Planck epoch in the atoms that make you the quantum uncertainty in every breath you take. I hope you remember that you are not separate from the cosmos. You are a piece of it, a particularly interesting piece capable of asking why. And if the question of what came before the Big Bang haunts you, good, let it. Not because haunting is pleasant, but because it's alive. It means you're thinking, wondering, pushing against the limits of what can be known. And that is what we were made to do. Not to have all the answers, but to ask all the questions. The Planck scale is the smallest distance, the briefest time, the edge of comprehensibility. But it's also a beginning. Not just the beginning of the universe, but the beginning of a conversation that's still happening between stars and dust, between mathematics and mystery, between the cosmos and the conscious minds it's somehow impossibly beautifully produced. We stand at the edge of wonder, not because we've run out of things to discover, but because we've discovered how much more there is to discover. The The universe is not smaller than we thought. It's deeper, stranger, more layered with meaning and mystery than any of us imagined. And so, we end where we began, with a quiet invitation. To rest, yes, but also to remain curious. To let the silence of the night remind you that beneath everything, beneath atoms and forces beneath space and time, there is something we can touch with thought but never fully grasp. And that something is not an absence, it's a presence. The presence of existence itself, humming quietly, asking to be noticed, asking to be wondered at. The Big Bang might have begun at the Planck scale, or it might have emerged from something even stranger. Either way, it gave us a universe capable of holding galaxies and fireflies, black holes and human hearts' equations and dreams. A universe where the smallest scale defines the largest questions, where mystery is not a bug, but a feature, and where beings made of stardust can look back at the stars and understand at least a little where they came from. That's enough. That's more than enough. That's everything. Thank you for traveling with me through these quiet spaces, through the mathematics of mystery and the physics of impossibility. Thank you for your curiosity, your patience, your willingness to sit with questions that have no easy answers. These journeys only matter because you're here to take them, and I'm grateful you chose to drift with me tonight. The universe has so many more stories to tell, more mysteries waiting in the dark, more questions hiding in the equations, more wonders humming just beyond the edge of what we understand. And I'll be here whenever you're ready to explore them together. Until then, rest easy knowing you are part of something ancient and vast and beautiful. Something that began perhaps at the Planck scale and continues now in you. Sleep well, dream gently, and know that the stars are still there, still shining, still asking to be understood. Good night.